Hi everyone. Thank you for joining our webinar, ETAP Getting Started for Project Management. This webinar will be the first part of a series of webinars that we will present with a focus on helping you get started with ETAP. Whether you are new to ETAP or looking for ways to save time and money with your power system projects, this webinar will present the most important features and powerful capabilities that allow you to quickly and efficiently tackle your power system analysis studies and increase your efficiency. Additionally, we will create webinars that focus and provide further in-depth detail on each solution you will learn about today. Typical project requirements. We all adhere to common project requirements as we look to finish the project within a schedule and budget. The requirements, from a high-level perspective, first consist of building a digital twin, as well as defining multiple revisions and scenarios that we need to analyze. As the project moves forward, we verify and validate different stages of the project, such as model creation and studies we perform. And ultimately, our final report, including results, our analysis, and any other information we'd like to highlight. In this case, we will discuss a large complex industrial system. The pain suffered through this process is what we will overcome by understanding available productivity-enhancing and time-saving solutions. Pains such as the length of time it takes to build a one-line diagram, the process and duration of validating the model. Sometimes the technology used has limits that need to be overcome, such as maximum data revisions allotted. And when all the scenarios are set up, it can be difficult to analyze these scenarios accurately and efficiently. When you are working on a large system, some old processes still practice waiting until one study is completely done before performing another study, which drastically affects the overall project timeline. This is an understandable process if you are using technology that doesn't have a great management system in place for concurrent studies and information sharing. Now let's go through our common situation we run into for large industrial projects. Please be aware we will be creating webinars for different industries such as transmission, distribution, and traction power systems. However, today's webinar will focus on industrial systems. In this case, we typically start with an old PDF of a large system. We start building the digital twin. However, while creating the one line, you end up receiving changes from the field verification crew. Also, different engineers are given the task to run studies based on their expertise. And then they have to consider adjustments based on the study they are performing. Impedance adjustments are implemented and changed based on study type. And because studies pull you in different directions, typically we wait till one person is done before you can finalize what you are doing. But this is not how we could be doing it with the correct processes in place, which we will learn about. One example of what I'm discussing is impedance. Impedance and load flow and short circuit have two different effects. Taking a conservative adjustment in load flow requires increasing the impedance, while the opposite is true for short circuit. And as these scenarios are created and updated, it causes project delays by sending information back and forth after the person has done their job. Waiting till one person done is already causing delays, but you create additional delays as more scenarios are developed. And then we have to repeat the scenarios that were just previously done. If you find, like for example, if you find yourself in need of an arc flash to change arc flash incident energy, we then have to go back to the protection and coordination study to evaluate our options. This is what happens when you don't have the solutions to perform arc flash and coordination concurrently. And these projects, in this case, can go from January till nearly October and take around 10 months to perform. We then analyze our results and document worst-case conditions. Any new approved modifications is sent to operations to update the system. And in the future, as the system changes, we will definitely be rerunning the scenarios we previously defined. Performing power system studies comprehensively, systematically, and accurately within the project timeline is critical to avoid unnecessary delays and profit loss. Understanding available productivity enhancing and time saving solutions and their underlying technology is essential to optimize project schedules, improve profit margins, realize higher project throughput, and extract the utmost value from your power system analysis software investment. The ETAP solutions we will discuss include the operation overview of ETAP, including the tools used in building a digital twin, running scenarios, and using Python scripts to run studies. We will also go over an overview of project management technology, including NetPM and the etapAPP. As the project continues and the analysis phase is upon us, we need to understand the use of result analyzers and rulebooks to evaluate limits and save time. Rulebooks are applied to automatically evaluate studies such as protection and coordination, as well as ArcFlash. We will be going over the ArcFlash auto evaluation solution and discover how much faster it is to evaluate incident energy limits during the protection and coordination phase of the project. We will also discover how using PlotView provides a plot interface that is not just a final deliverable, but a method to evaluate results as studies are performed. Let's review the project schedule one more time, which lasts from January to October, before taking a look at the new schedule created by using the latest ETAP solutions we just discussed. This project schedule requires us to include sequential, recirculation, and repetition of studies due to conflicting project solutions. With our new project schedule, we have multiple individuals working on the project at the same time and submitting their updates so all affected engineers can work off the latest model, as to have it updated and validated at all times. Also, the modeling, validation, and engineering phases are reduced further by utilizing the solutions we are about to present. This reduces the timeline of this project by nearly 5 months. It is now time to learn about the technology that gets us there. Before we review the most efficient way to build a digital twin of your system, I would like to discuss a few ways to visualize a system that originates from GIS. If you have your system modeled in a geospatial diagram, you can bring that into ETAP and automatically generate multiple views, including a feeder view and a net view, as well as the substation view many people are already familiar with and utilize. This project has a GIS system and includes ETAP NetView. ETAP Intelligent Geospatial Diagram provides an editable environment for electrical assets and connectivity combined with geospatial data. Geospatial information can be imported from many third-party systems or can be modeled directly within the electrical geospatial diagram. NetView is automatically created from GIS and represents a model that displays the network highlighting the substation connections. The substations are easily identified along with the switches and breakers while removing all the details included in the feeder. The ETAP presentations are in sync, so if I click a feeder in NetView, the same feeder is highlighted and selected in GIS, so you can easily track the portion of the system you are analyzing in each view with respect to each other. I can also run unbalanced load flow as well as additional studies on both views. If you would like to see a more detailed look into the feeder, we can select the feeder view from GIS. This visualization represents the details of the feeder and provides results and information on equipment that is connected to the feeder. With the GIS feeder view, network view, and substation view, we get a clear understanding of the entire electrical system. Let's take a look at this entire model from within ETAP NetView. We can easily identify the substation connections. Substations are indicated in green. Switches and breakers are indicated in red. This makes a complex electrical geospatial diagram very easy to follow. And to see the details of any substation, all I have to do is click one. This is the type of visualization many people are familiar with, and the type we'll be using for the rest of this presentation. Now I'm going to be creating a new model, but before we create this model, let's define the rules used to build our one-line diagram. The ETAP rulebook editor allows us to define the preferred spacing between any two devices. So you can review the default one set, or adjust them for your own preferences. And we can enable the voltages that we will use for this project. And from here, I can quickly build my one-line diagram. As I click each device, it automatically connects with the spacing I identified in the rulebook. I have options to center align. Then I can select all of the motors, click a low voltage circuit breaker, and it auto inserts above each motor selected. You can auto insert any device in ETAP. Then we can simply begin to add motor information. And now I can use keyboard shortcuts to paste this information to my other devices. Select my anchor device and click Shift-C. And it asks me if I'm sure if I want to replicate the properties of motor 9 to other selected elements. And this instantly pastes the data from motor 9 to all other selected motors. And if you happen to have an existing model that you would like to improve the look and feel, don't forget to take advantage of the alignment tools provided by ETAP. Also, make sure to take advantage of the pre-built templates that ETAP provides. There may be templates that are very similar to what you need to construct. And if you find yourself that you've built, for example, an MCC that you use and is a common structure, you can save what you created to a template so anyone in your company can take advantage at any time. Now, the system I just built is a pretty easy example of how to create the one line. But in a large complex industrial system, you have different people working on it at the same time, and you have to consider changes that are consistently being made. Here's where project management comes in. Now, the tools I'm about to explain include an etapAPP for data collection and verification, and NetPM, which allows you to collaborate from anywhere, and contains a built-in review and approval process, and streamlines your processes for simultaneous modeling and analysis. In this example, we have two projects synced to NetPM. One is the master, and one is the client. You can simply make changes at the master project. For example, this transformer. Changes as simple as ID updates, rating updates. And if we look at the client, you'll notice the IDs on the one line were automatically updated. These two projects are in auto sync. Any change you make from the client or the master automatically updates the rest of the ETAPs that are synced with this project. Whether I make additions or in this example deletion, you will see the immediate update of the client project. Breaker configurations are also included. NetPM can be set to auto, which we previously saw, or supervisory mode. In supervisory mode, as this example shows, the user adds a load, and that addition or any changes is saved to the project editor. Now a request has been sent to the project manager. After review of the proposed changes, the project manager can then approve those changes to incorporate into the master project. Now, this is a very high-level summary of NetPM. If you do go to the list of ETAP webinars, we do have a very in-depth webinar on NetPM that you can watch. NetPM allows us to move from sequential to parallel power system modeling and analysis. We can now do simultaneous multi-user model creation, data collection, and validation, and bring all of this information together through a private or public cloud network. This syncs the ETAP desktops as well as the ETAP apps that are out on the field and provides project managers the necessary tools to review changes and accept or reject decisions based on their decision. And since information is shared on the fly, this allows engineers to perform concurrent system studies, analysis, and reports. And once it's time to run our studies, we could take advantage of our scenarios. And incorporated in the scenarios is revisions that manage all the electrical data properties that you can alter and have unlimited layers. You can change cable lengths, transformer taps, anything you like, and incorporate it into an electrical revision layer. Configurations, which manages the status of protective devices, switches, open and closed, which position, and mix and match any for all of the study types provided in ETAP and run it through our scenario. An additional way to run studies is through Python scripting. ETAP provides a Python script API. This API interfaces with different ETAP clients to run scripts using Python language. The Python window uses the IP address to connect to your projects, which ultimately means you can run scripts to ETAP projects that reside on different PCs from one location. You can also enter command lines, such as help. You can also open scripts that you have already written in the past, recall them. So in this case, I'm opening a script that I've created for time domain load flow. And once selected, it runs the script, which then triggers a command in ETAP to run time domain load flow and immediately open the result plots that were selected. You can open plots, Excel reports, or just show the results on the one-line diagram. So if I wanted to see this for a different study, I can simply go back to my Python script and then open one that I created for load flow with commands. The command in this case would be to open a breaker. So the script is printing row flow and is running the load flow. The breaker is opened and the results are displayed in a plot view. You can use a keyboard shortcut F5 to run the script at any time. Since we are discussing plots, I'm going to also run a transient stability study. Bring up the plots for generator 1, and we can now visualize the results of generator 1 from ETAP PlotView. I have all the selected plots laid out. And as they're activated, I can switch to study case editor and run a different scenario. And when these plots are in live, you can see the new scenario results embedded in the same plot while still hosting the previous scenario's results. So you can compare them side by side on the same plot. And while running studies, we can right-click on the generator itself, select one of the plots we'd like to keep, and host that plot on the one-line diagram. That way, as we're running studies, you can always see the latest plotted results for, in this example, a generator real power. And PlotView allows us to customize the look and feel of the plot to however you want to set it based on the user's preferences. You also have the ability to export the data to Excel or copy data to clipboard to use in your final output report deliverable. And we can align as many plots as we like on the one-line diagram. So I can create an additional plot for sub 3 bus, and here I decide that I want to see the voltage. And when we are done running our studies, it's time to evaluate the results. To evaluate coordination, protection, and arc flash, we're going to use Star Auto as well as Arc Flash Auto. Star Auto is an automated and protection coordination solution which provides automatic detection and evaluation of system protection and coordination based on customized design criteria and industry guidelines. You can easily identify false tripping and miscoordination, avoid mistakes, reduce laborious hours of reviews, and all this is standardized against industry rules and guidelines for system protection and coordination. Rule-based criteria help us quickly resolve conflicts between bolted and arcing faults. And Arc Flash Auto provides an automated evaluation against arc flash energy limits. To incorporate the bus in an Arc Flash Auto evaluation, we're going to go to the Arc Flash tab, go to TCC Plot Energy and select C Area. And from there, we're going to select the C Area settings. You can provide this information or use sample data. In this case, I'm going to use sample data. I'm going to select to do protection and coordination on T2 and sub 2A. So we run Star Auto, and as the system evaluates the rules defined in our rule books, we get a tabular list of results. Now I can look at my protection and see for this transformer, I have an issue with the pickup limit, and it tells me what the issue is. It says it's 420 full load amps, which is below, or it's 390, which is below the 420 limit. And then I can go to Arc Flash, and I see that the C area is within its appropriate limits. If I select CB2, it'll give me the actual bus protection. Or I can click line side, and the TCC automatically updates to show the line side limits against the protective device. Now we can adjust the settings of the protective device, and Auto Arc Flash will automatically update the results and display any errors or messages based on the new settings. Auto Arc Flash evaluates conditions which are literally impossible to evaluate with a typical Arc Flash study. It also significantly reduces the number of Arc Flash study scenarios required. This increases safety and reduces labor-intensive data collection for each piece of equipment. I can also open it directly from the C area, open the bus editor, enable the damage point, and within that same TCC, I can see sub 2A's arc energy damage point on the curve. This helps me easily evaluate if my protection and coordination are appropriate for arc flash incident energy limits. The arc energy damage point is based on ANSI C37.20.7, arc resistant equipment damage point. And based on these limits from these standards, we can also evaluate if this is protected appropriately as well. And as shown in the arc flash result analyzer, sub 2A is within all arc flash incident energy limits. Data blocks on the one line can also be used to display results. I can customize a data block by double-clicking the existing data blocks or using the data block editor. Here we can incorporate properties or results and any combo of both into a data block, and I can choose to include them or exclude them at any given time. I can also select the properties of which I want to include for my tooltips. That way, if I temporarily hover over a piece of equipment, I can get properties that I don't necessarily need to be permanently on my one line. Now, when I'm ready with all my scenarios and revisions and I've ran all my cases, I quickly want to identify worst case conditions. So in Arc Flash mode, I can open the result analyzer and look at the results for all of my equipment and quickly identify with one click of a button my worst case condition, my worst case scenario for each equipment. The result analyzer allows me to filter by equipment type. So if I just wanted to see buses, I could just select buses. If I wanted to see the source PDs, we can bring those in. If I wanted to filter information by connected bus, I can bring that to my result analyzer and sort by connected bus. This way, each piece of equipment is associated near the same piece of equipment that it's connected to. And as my final deliverable, if I want my data block to show worst case conditions, I simply click Update Data Block on the result analyzer, and the one-line diagram results will be reflective of the worst case condition for each piece of equipment. In this case, sub 3 is currently at 6.14 calories per centimeter squared. And when I select Update from Data Blocks worst case condition, you'll see it's now updated to 6.255 as my worst case scenario result for my final deliverable. And instead of recreating this model for a different SCADA system, you can leverage ETAP's Smart Digital Twin from design to operations. With embedded predictive analytics, adaptive optimization algorithms, and action validation to ensure fast, safe, comprehensive, and reliable operations. ETAP predictive simulation gives engineers and operators the ability to perform accurate analysis by using actual operating values in their studies. This information can be used to prevent system interruption, identify causes of operational problems, as well as validate system settings. The Smart Digital Twin can also be used as an operator training simulator. With ETAP Real-Time, we can monitor data on the one-line diagram. This provides an intuitive, intelligent, integrated real-time monitoring solution for predictive simulation. Or we can use ETAP SCADA to create our views and highlight critical equipment. In this data center, we are monitoring all the PDU power. Another view allows me to see a high-level overview of the power system with connectivities, similar to our one-line diagram. And this ETAP SCADA view incorporates the scenarios we created in our engineering phase, allowing us to run these studies via online web interface. We have discussed many ETAP solutions required for the operation of ETAP, project management, and time-saving rule-based evaluation and result analyzers that are incorporated into a project to ultimately enhance productivity and reduce project completion time. This is part one of the ETAP Getting Started webinar series. We will be sending further webinar announcements that include new products as well as tutorials that provide an in-depth education on each of the solutions we discussed today. Thank you again for joining and watching.